Good afternoon, and thank you for joining CPCI's webinar on using precast concrete as a smart building asset. Today's presentation will be approximately 55 minutes in length. We will be answering questions at the end of the presentation during the Q&A session. The webinar will be presented by Tom Machinchik, presenting on behalf of ThermoBuild. Here is Tom Machinchik.
Thank you very much, Ariane. I'm very happy to be here today to present a presentation on precast concrete as a smart building asset using integrated ventilation solutions. My name is Tom Machinchik. I've spent the past 10 years in the intelligent buildings industry working for several leading market research firms, including Navigant Research and Consulting, Pike Research, and Manifest Mind. I joined ThermoBuild earlier this year because I felt that it was one of the best technologies that I've come across in my market research over the past 10 years, and I wanted to help promote it in the buildings industry more widely. Without further ado, we'll go to the learning objectives for this session. We will understand the value that concrete and hollow core precast concrete slabs present to the sustainable buildings construction industry, how to actively engage the dormant properties of concrete and concrete hollow core flooring slabs through integrated ventilation design, substantiate the value of integrated ventilation design to fill the gap that exists in the market. We'll learn more about the applications and components of an integrated ventilation smart floor kit, and also discuss how to position your concrete and concrete hollow core slabs as an attractive, sustainable building material for new construction and retrofits for low energy or net zero/intelligent buildings. As an introduction, we'll be discussing once again the value of integrating precast concrete hollow core flooring slabs with building ventilation systems. When the thermal benefits of concrete are actively managed and integrated with the building's ventilation system, it is one of the most sustainable materials in the industry. Now, the picture to the right shows a brief example of an installed integrated ventilation design during construction, while the inset picture is a close-up diagram of a modified hollow core slab. More details will be provided as this discussion moves along. Before we continue, however, I'd like to mention a few items. First, that this is proven technology. ThermoBuild has a 15-year track record, 35 completed projects, over 2 million square feet of buildings, and 4 LEED certified buildings. We've won a number of awards in the industry, including being identified as having the 2 best performing schools in Canada awards. You can see the document here at the bottom right for sustainable schools. That's the research paper that was produced as part of that initiative. We also have the best performing net positive school in Horry County, South Carolina. This is a campus of 5 buildings and was actually featured along with our 2 Canadian schools in a recent NREL research report called A Guide to Zero Energy and Zero Energy Ready K-12 Schools. All of our energy use intensity figures are well below United States Department of Energy building type averages for various ASHRAE climate zones. Code compliance, integrated ventilation design complies with all national and local codes and standards where applicable. Unique local codes have never presented an issue for us. And this is a design assist. We do not manufacture or sell any components. We don't write or maintain software. There are no new skills required to install or maintain an integrated ventilation design, and there's no unique equipment sets or components required for the installation of integrated ventilation design. We use standard off-the-shelf equipment, and this gives the architects, designers, and engineers for any specific project the flexibility that they need or desire to use the equipment that they're familiar with, vendors that they're familiar with. So there's nothing new that's required or out of standard, basically off-the-shelf equipment. I'd like to mention a few key building initiatives in the industry today. Integrated ventilation design assists with all of the current building initiatives in the architectural, engineering, and construction industry. These include net zero electrical energy, net zero or zero net energy, zero net carbon, embedded and operational carbon, and smart city initiatives when they become available or implemented in various different locations across the globe. Buildings for smart city initiatives need to be grid connected, responsive, resilient, and efficient. and integrated ventilation design ticks all these boxes for those characteristics for a smart city building. The main feature can be seen here at the top, especially in today's world with the COVID pandemic. Integrated ventilation design significantly reduces the spread of communicable diseases. Most of the year, integrated ventilation design uses nearly 100% outdoor fresh air to condition the indoor spaces of a building. So there's enhanced air quality. The building does not have sick building syndrome, so you'll have a healthy building. And in various industry studies with higher air quality, productivity of employees, and just a better feeling, a better atmosphere at a home in a residential setting can all be enabled through integrated ventilation design. So what is integrated ventilation design? You can see in this graphic here is a explosion of a CAD drawing. The inset shows that the slabs are installed in a standard manner. However, they are massaged in a way that some of the end caps are closed off so that we can create this labyrinth of ducting within the hollow core slab. Simple L ducts are used to connect the hollow core slabs with the ventilation, the serpentine ducting installed inside. These connect to the main HVAC duct and supply air into the building through a standard diffuser. The changes that are made to the hollow core slabs can be done on site. It's a very simple operation. Once the construction crew is instructed in how and where to place the various different things that are needed to be done to the hollow core slabs, it becomes like an assembly line process. We can also have these things manufactured at the concrete manufacturer itself, and the concrete hollow core slabs can be provided to the construction site as a smart floor kit. So if we look at a typical design process in the building industry today, most buildings start with a standard building structure, and then once the structure is identified, add-on equipment, which is more costly and generally more complex, is added to the building structure to enable its performance and ideally greater efficiencies. The one thing that happens in this type of design process, however, is that the structure of the building itself is ignored. And if we see that the benefits of the structure itself, especially if it's made out of concrete, this diagram shows the thermal storage potential of various materials. And you can see that the concrete is far and above other common construction materials, including wood, light concrete, and brick. It's a little bit lower than stone, but stone is much harder to work with. So concrete has the advantages of being easy to work with, but it also holds enormous thermal storage potential over other materials. In addition to its thermal storage potential, it also offers the building extreme weather safety, radiant comfort, air quality, deeper efficiencies, and extreme building resilience. So everybody is aware of the passive thermal benefits of concrete. They are well known. The passive benefits can be thought of as sunlight shining on a concrete floor, which absorbs the energy from the sunlight. And then at night when the sun goes down, the heat from the concrete can, radiate the heat back into the indoor space, providing some benefit. But this benefit is generally smaller. If these thermal benefits are actively accessed, it unlocks significantly more opportunities for efficiencies, cost savings, and carbon reductions. So active management of concrete has an effect on building comfort and performance, and it turns the concrete into a smart building asset. So you're actually getting value from your building structure. It's not just there to basically hold up the building. So if we look at the same building design process with integrated ventilation design, we see that the thermal storage potential of the structure of the building requires less HVAC systems. So the HVAC system can be reduced because much of the thermal energy within the building is being stored in the structure itself. And the costly and more complex add-on equipment is not So dedicated outdoor air systems, chilled beams, ice storage, sensors, and radiant in-floor heating can be eliminated. Baseline building will perform as good or better without the added cost. In fact, the building will actually be less expensive through the reduction of the HVAC system and the elimination of these extraneous systems. The main point that we'd like to emphasize is a quote by Paul Porcellini of the NREL Research Group. You can't just design the building, throw in some energy features, and then see how you did. The energy and architecture have to work together to meet the objectives. And that's exactly what integrated ventilation design is. So if we look at a real world example, the left side of this graphic in the picture here shows a building, a LEED Platinum Net Zero building that has solar, chilled beams, radiant in-floor heating, and chilled water tanks as part of its solution. The building on the right-hand side of this graphic has none of these advanced ECMs, energy conservation measures, and less solar. And at the bottom here, we have some statistics for the left-hand side of the graphic and the right-hand side of the graphic. And you can see that the integrated ventilation design performs better with less equipment in the building, saving in cost, complexity, and adding tenant comfort to the situation. So in a real world example, without the complexities of the advanced energy conservation measures, integrated ventilation design actually performs better. To look at some other of the cost statistics, a standard building compared to a ThermoBuild building with regard to capital expenditures for initial construction, integrated ventilation design allows the capital expenditures for a building to be $10 to $50 per square foot less than a standard building. And this is due to reduction in the size of the HVAC system itself, the elimination of some ducting like perimeter ducting. Drop ceilings are not needed anymore because the concrete serves as the floor and the ceiling of the building. They can be allowed, but they're not necessary. So there's significant cost savings that can be attained during the construction and design phase of a building when compared to a standard building. With regard to life cycle costs, the Building Owners and Management Association has an operational expenditure or OPEX factor. A standard building has a factor of 3.0. And what that means is that if your building cost $100 million, over the life cycle of the building, the OPEX for that building will be $300 million. With a ThermoBuild or integrated ventilation design building, this factor drops to 1.8, which means that for your $100 million building, your operational expenditures will be reduced from $300 million to $180 million over the life of the building. Energy consumption results, we'll see energy reduction expenditures of 35 to 50% in savings, and the HVAC performance of 40 to 50%. There are many additional benefits that come along with integrated ventilation design. These are not add-ons. These actually come with the system. These are things that happen just as a natural effect of having integrated ventilation design in your building. The first and maybe the most important is the tenant comfort. Everyone knows the value of radiant comfort. Most radiant systems are hydronic, meaning there's water flowing through pipes, and it's only in heating mode that this can be experienced. With integrated ventilation design, it's both heating and cooling mode, and it's air-driven. There's no water or water pipes to lay in the floors or anything else like that. So it's simpler, and it works in both heating and cooling modes. This system works almost entirely throughout the year with 100% natural outdoor air flowing into the building. They call these systems dedicated outdoor air systems, and integrated ventilation design throughout the year uses outdoor fresh air to condition the indoor spaces. And this is due to the fact that the heating and cooling energy can be stored in the concrete systems, the thermal cap. When outside air is brought through the ducting that goes through the concrete floors, the air coming into the space it's at a temperature that is ideal for the set point that you have set in the building. There's less noise because there is less velocity of the air coming out of the ductwork. Forced air ventilation systems generally have an on mode or an off mode, so the ventilation system at a higher velocity. With integrated ventilation design, the air can come out at the same high velocity if necessary, so there's less noise and less discomfort and mixing of air within the space. Cold and warm calls are virtually eliminated because the temperatures in the building drift very slowly. With forced air ventilation, the temperature will drift down to the bottom set point. The heating or cooling elements come on to lift the temperature back up into the comfort zone. So there's spikes and valleys, or peaks and valleys of the temperature, and actually the comfort of the occupants. Integrated ventilation design building, the temperature drifts very slowly. There's less noticeable effect of the heating and cooling element of the HVAC system with integrated ventilation design. As far as complexity of the buildings can be less complex if desired. There's no need for any complex systems. However, they can be used if you desire greater efficiency. So as a baseline, integrated ventilation design will give you a higher performing baseline of the building. If you'd like to add more complex, say, digital efficiency tools, you can do that. Your building will just be more efficient. With less complexity comes lower personnel costs. You don't have to hire more people. You don't have to train them to work with some of these more complex systems. Building systems become very simple, which reduces the cost for maintenance, reduces the cost for parts for various different building systems, and overall your building operates at 40% less than a standard building. Concrete structures are very resilient and very safe. With integrated ventilation design, buildings can be identified as an emergency shelter during disaster situations or other local emergencies. The temperatures of the building or indoor comfort of the building can be maintained for up to 3 days due to the thermal capacity of the concrete in the building. And also the ventilation system is largely driven with variable speed fans, which can be run from a very small backup electricity system versus a larger system. Brownouts and blackouts, the effects of those are lessened due to the thermal qualities, once again, of the concrete. So there's less work-life disruptions, whether the building is in an office or a commercial setting or a residential setting. There's less disruption to whatever use the building is being used for. And once again, just like to stress that communicable diseases, the spread of these are drastically lessened for a variety of reasons. The mixing of the air in the building due to the fans and the use of the ventilation system, as well as the nearly 100% use of outdoor air to condition the indoor environment of the building. 7 to 13% of the building space can be saved. There's no need for drop ceilings. Over the course of, say, a 50-story building, if you're eliminating drop ceilings, the saving of that 1.5 to 2 feet of space can add up to maybe 1 or 2 or 3 or more floors, which brings additional revenues to the building owners and operators. With regard to the designers and the engineers and the architects for a building, you can have higher ceilings, which to the comfort, but to the aesthetics of the building. And this space savings can be used for storage or other uses. We mentioned a few of the characteristics of aesthetics. Designers have a lot more options. Perimeter ducting can be removed. It isn't necessary because the ventilation system is stored in the floor and the ceiling of the building. So you can have higher ceilings, larger windows, less ducting along the perimeter, and that gives the designers and the architects more options. And finally, there are many financial benefits that can be realized by taking advantage of, say, utility demand response programs, energy efficiency credits, net zero and net positive buildings, which we spoke about previously, and also time of use pricing. With integrated ventilation design, there are significant avoided costs. We can remediate over budget situations for a construction project due to the cost savings that we provide during the design process, and we also offer a design performance guarantee. This is another picture of the design process of a building. On the left-hand side, we have energy use intensity figures in thousands of BTUs per square foot. These are identified in ranges due to variations in the type of project or the climate zone. The point of this slide is to identify that the building starts at the top of the energy use intensity scale. So most buildings start here as far as their performance is concerned. The next thing that happens is the equipment is added. So we'll add to building envelopes, say with ICF concrete for insulation, a simple HVAC system, and some high-performing windows. To get to the next level down, we can add high-performance HVAC systems, LED lighting, and other pieces of equipment similar to that. Once again, moving down the ladder, we can add energy management systems, sensors, other digital energy conservation measures. And this is basically a different way of looking at the process, the building design process that we saw in slides previously. The point that we'd like to make here is that an integrated ventilation design building, the baseline starts at the lower rung of these ladders for $10 to $50 per square foot less in CapEx. So these pieces of equipment do not need to be added to get a better performing baseline for a building. To get to net zero, either of these buildings will add solar to get to net zero energy. They can add more solar and actually have a net positive building. Integrated ventilation design will allow smaller solar by up to 25%. This may be one of the most important slides of this presentation. You can see on the left a ThermoBuild building. During the winter months, all day from 4 degrees Fahrenheit to 17 degrees Fahrenheit, the heating system did not even come on during the critical part of the day, and actually the most expensive time of the day as far as utility electricity pricing is concerned. If we look at the top portion of this left-hand graphic, you can see that even though the heating system did not come on during the day, the temperature drifted very slowly upward during the day. And the reason for that is the concrete hollow core slabs are absorbing the heat energy and the load from occupants of the building, the lighting system in the building, and other equipment that is in the building. Now contrast that on the right with a conventional building. You can see that during the day, the heating valve was coming on and off, on and off, on and off to meet our temperature requirements of the building to keep the occupants comfortable. But one thing to notice is that the temperature, along with the on and off of the heating system, the temperature rose and fell and rose and fell and rose and fell. And this can be uncomfortable for occupants of the building. So one minute you could be hot, the next minute you could be cold, next minute you're hot. Whereas in a ThermoBuild building, you could see the slow drift. So the temperature changes are barely noticeable, and indoor comfort is maintained throughout the day. Heating system did not even come out on throughout the day, even with very low temperatures outside. This graphic identifies a person in a hallway in a building. You could see the labyrinth of the ductwork that was placed inside the hollow core slab up near number 3 here at the top of the right-hand graphic. And the air comes from the main HVAC duct through the concrete into the space or the room. You can also see that the flooring of the building has the same labyrinth, but one thing that I wanted to point out here is that these diffusers that are coming into the room can actually be reversed. So the diffuser can have ventilation coming from the floor of the room into the various different spaces in the building versus coming from above. This shows a inset diagram of a modified hollow core slab. Once again, this is the labyrinth within the hollow core slab where it comes in from the HVAC system and exits into the building space with a standard diffuser. Please note that in heating mode or cooling mode, the temperature of the air that is coming through the slab gets conditioned by the stored energy that's in the concrete, and it comes out at the desired temperature of the room. So we're not forcing air out that's 95 degrees to mix with 60-degree air to get your comfortable temperature. We're actually conditioning the air before it comes into the room, and it's coming out into the room at the temperature that is desired for comfort of the occupants. This is a graphic of what happens with a human standing in a room. With radiant systems, people are cooled by radiant heat transfer from their bodies to adjacent surfaces and ceilings, whose temperatures are held a few degrees cooler than ambient. So if you have the input air ducting along the floor, displacement ventilation, the heat from the people and the equipment in the buildings rises and it's exited through the top of the building. This is a very comfortable situation, which we'll see further along in the discussion. This is just a depiction of how the concrete can absorb the energy from a human being or from lights or equipment. So during occupied hours, heat from internal loads is absorbed by the precast concrete slabs. And during unoccupied hours, cool nighttime air is circulated through the slab to remove the heat that was stored during the day from the equipment and the bodies and the occupants of the building, and it's pre-cooling the space for the next day. In heating season, during occupied hours, heat from internal loads is transferred to the hollow core slabs through radiation. During unoccupied hours, if the hollow core slab cools down below the set point, the air handling system is started in recirculation mode. So during the day, the heat from the occupants and the equipment is stored in the concrete, and at night, the ventilation system comes on to use that preheated concrete to heat the rest of the building without accessing the heating elements of the HVAC system. And this is how the building can operate throughout the year in fresh air mode versus turning on the heating and cooling elements, which are significantly more costly. One very interesting fact about integrated ventilation design buildings, of the 35 building portfolio that has been built so far, over 30 of the buildings act as a dedicated outdoor air system without an energy use penalty throughout most of the year. This is true in most climate zones, but in some climate zones, the only reason the building would require an HVAC system is because of the local codes. Other than that, it literally can operate throughout the year in outdoor air ventilation mode. The box on the left shows some ASHRAE statements on airborne transmission of SARS and COVID-19. Basically say that you should not turn off your HVAC system and it should not be really modified too much. However, that can be dangerous in most buildings because most buildings just recirculate the stale air throughout the building. So it's a big challenge for the industry today. However, integrated ventilation design can solve this by using fresh outdoor air for most of the year. We can see this in an actual setting. These two buildings in this graph are measuring the CO2 levels for a conventional building and an integrated ventilation design. Conventional building is the darker chart boxes. Integrated ventilation design is the lighter green elements. You can see that the building for integrated ventilation design never rose above the max CO2 allowed, while the other building did several times throughout the day and almost 4 times throughout the day. These buildings can be used as a valid argument because these two buildings actually sit next door to each other. One has integrated ventilation design, the other one doesn't. So the danger of a standard forced air ventilation system can be seen in the left-hand part of this graph. The air is coming out as a high velocity from above. It's mixing with the air in the room, and this beaker represents a room and a person in the room. So this air is mixed together. If this is recirculated air, contamination, diseases, air particles from other parts of the building can be actually put into every room in the building if it's in recirculation mode. With integrated ventilation design and displacement ventilation, which comes from the bottom, we keep the comfortable air where the people are, and we exhaust the stale air and potentially diseased air out through the top of the ventilation system and out of the building, whereas fresh air comes in from the outdoors, is passed through the concrete conditioned, and comes into the space in a very, very comfortable way. And is placed where the people actually are in the rooms. So warm air has buoyancy. We allow the air to transport itself. We put the treated air where the people are located that are closer to the floor, and we don't have the velocity of the ventilation system that a standard forced air system has. So it keeps the occupants more comfortable and safer. Generally, air recirculation with integrated ventilation design is only used overnight when the building is unoccupied, and is used in the winter when heating is needed and in hot climates when night pre-cooling is required. So this is one of the safest ways to maintain disease-free environment within a building, is to reduce or eliminate recirculation of air in the building while supplying fresh air to the building most of the time. If we could look at two different pictures of a conventional ventilation system and a radiant air conditioning system with a thermal imaging camera, we could see that the image on the left is seeping much of the heat that was brought into the building outside through the building envelope. This is very inefficient, and one of the reasons this happens is because the perimeter ducting along the walls, which is necessary to maintain comfort, is also very good at letting that heat that you paid for escape through the building envelope. The graphic on the right shows an integrated ventilation design where hardly any of the heat is escaping, and that's because the thermal energy comfort systems of the building is stored in the flooring and the ceilings of the building. It's not being vented anywhere near the building envelope. So the comfort within the building is maintained, and you're also saving quite a bit of money without heating the outdoor environment outside of the building. This is a diagram of a typical condo unit. Thing I'd like to point out on this graphic is the perimeter venting that needs to be used to keep the space comfortable. This not only is costly and unnecessary if you use integrated ventilation design, but it is necessary to keep the comfort of the building within the condo. It also takes up space to enclose this, limiting the options of the designers, the architects, and the engineers that are putting this building together. We contrast this same diagram with a integrated ventilation design. The perimeter ducting that I mentioned on the previous graph can be eliminated. You see the X's here, and this is one of the things that we do during the design process is we take building systems and either reduce them or eliminate them because they're not needed anymore. This is the ductwork that would be necessary for an integrated ventilation design represented in the red. So there's less ducting, and there's also less intrusion into the space of the building where the occupants can have better aesthetics, higher ceilings. You can actually have higher ceilings if you like, or you can maintain ceiling height and just get rid of the drop ceilings to gain some space and possibly additional floors and save money that way when you're constructing the building. Once again, there's typical thermostats and diffusers that ventilate into the room to maintain indoor air quality and comfort. So the two schools that I mentioned way back in the beginning of this discussion, the Mundy's Bay and the Hyde Park schools in Canada, the two most efficient in Canada. This graph was created by Intermodal Engineering, so Thermobuild did not create this graph. This is an independent audit of the performance of the Mundy's Bay school. To compare to more average figures of schools, I'll go through some of what this chart says. The leftmost bar in this graph is the energy's intensity in thousands of BTUs per square foot of education buildings in North America. The second one is education and secondary schools in Canada overall. This is the education and secondary schools in Ontario. And this is the baseline performance of the Mundy's Bay School without integrated ventilation design. And this was simulated or modeled on building simulation software. This is the modeled building after integration ventilation design was instilled into the design itself and then modeled. So you can see that this 47 kBTU per square foot figure is much lower than the standard building in the modeling. The actual results turned out to be 43 kBTUs per square foot. And the reason for the difference from the model to actual performance is the models don't pick up the gain that is attained by absorbing the heat from the occupants and the equipment in the building. So the actual performance of the building was better than what the model said it was going to be. And to the right, we have an extremely efficient school with really no advanced ECMs coming in at 28 kBTUs per square foot, once again in Canada in climate zone 7. Both of these buildings can be considered net zero ready by any standards in any climate zone in the country. If this was in climate zone 4, for example, this figure may be even lower. Integrated ventilation design is compatible with many different unique design solutions, including biofilter walls, solar thermal and night sky cooling, reduced geothermal. So with standard geothermal, one of the benefits is that the size of the geothermal field can be reduced. And this may be applicable to many different buildings, but especially in buildings that have a limited outdoor acreage to put the building up. They may not have enough outdoor space to actually drill this full-size geothermal field. If that's the case, then if they used integrated ventilation design, this geothermal field can be significantly smaller. No new substations. An example of this is a building that was being constructed in a standard fashion with various different energy consuming efficiency components like ice storage or, for example. The building designers found out that they did not have enough electricity coming into the building for the substation that was already there. They would have to add an additional substation to manage the electricity for the building and all the components that they wanted in it. When they used integrated ventilation design for the building, they realized that less electricity was needed and they didn't need to add the extra substation. So that's a several $100,000 savings right there in the construction of the building. We have a variety of different Canadian project examples, and these projects can be found on the ThermoBuild website or upon request. So I encourage you to go to our website or contact CPCI to get this information. So integrated ventilation design are net zero and net positive ready as a baseline. So once again, the complex energy conservation measures do not have to be added to integrated ventilation design to get them to a net zero or net positive ready status. Integrated ventilation design buildings are also smart city and grid interactive ready as soon as local initiatives are implemented. To the right, we see pictures of the Horry County School in South Carolina. These are pictures of the various different buildings on that campus. So the next few slides will be pictures of actual pictures from the real world. On this slide here, we see a completed system with exposed ducting. And the center and the right pictures show an integrated ventilation design that is under construction without the completion of the ceilings or floors. Once again, the picture on the left here is a completed installation. You can see the exposed ducting here. This is in a school setting, and the pictures to the right connecting to the main HVAC trunk with these smaller L ducts. This slide in the top right-hand corner shows a displacement ventilation where the air comes into the room from the bottom instead of the top of the room. And this is just an end of one of the main HVAC ducts. These are two different settings. The left picture is a completed system in a healthcare building in Canada. They're taking advantage of the fresh air that is brought into the building, especially in a healthcare setting. This is very, very important so that diseases or communicable diseases or bad stale air is exhausted from the building, while keeping the indoor comfort conditions at the right place, using just outside fresh air. The picture to the right shows the effects that integrated ventilation design can have on the perimeter of the building. Notice that there's no ducting on the right-hand side above these windows here. And the ceiling can be allowed to be higher. And in a work situation, higher the better the space is for productivity. It just makes a nicer, more comfortable space. These are various different pictures. I won't talk about them individually, but you could see integrated ventilation design used in common areas, which can be extremely large. We have a setting in a library here, so the quietness and the comfort of the integrated ventilation design can be used in a variety of different settings, taking into mind the aesthetics of the situation and also the indoor air quality and comfort that integrated ventilation design offers. Wanted to point the listeners to a variety of different papers and case studies Once again, the case study identified on the right can be found on our website, termobuild.com. And this study, Designing Buildings for Post-Disaster Resilience with Thermoactive Radiant Air Conditioning Systems, the paper produced by the president of ThermoBuild, Jack Lakin, and this can be found on the cpci.ca website. I want to thank all the viewers today for your interest and for taking the time to watch this presentation on integrated ventilation design. I hope you enjoyed the presentation. Hope you learned something, and obviously you can reach out to Jack Lakin, myself, or CPCI if you have any questions or things that you would like to discuss about integrated ventilation design. So thank you for attending. All right, we have some great questions, and I'd like to have Jack Lakin, who's the president of ThermoBuild, answer them. He's the head engineer for projects that we do for integrated ventilation design. So I'll start with the first question. Can you describe the engagement process that ThermoBuild uses to work with a construction project design and engineering team?
Sure. Thank you for the question. Usually it starts with a design brief for the project, and the aim is to enhance the outcome by basically using the design brief as a reference point to engage the heating, cooling, and ventilation with ventilated concrete floors. And the aim is basically to drive simplification.
So you interact with the design team at the architect or engineering firm and take their designs and basically just modify them to include the integrated ventilation design?
Right. The modification usually takes place in reduced need for heating and cooling capacities. It doesn't change the architectural floor plans other than basically adds a simplification to drive higher and better outcomes of the building. The reason why our design assist is required for the better outcomes is the fact that the conventional engineers do not have the software that takes into account the value of the dormant concrete engaged as a smart asset. This is a technology that has been developed over the last 15 years, proven successfully, and has been independently validated with best performing buildings in Canada, most recently in the United States.
Here's another question that we have. When you say that integrated ventilation design acts like a dedicated outdoor air system most of the year, what do you mean by that?
Yes. That's a great question. What is interesting, when we engage the dormant asset in a building, like the ventilated concrete floors, it works like a smart asset that is capable of harnessing low-grade energy that otherwise is not engaged by conventional systems. So usually the building can operate about 70% of the year in a natural mode. It means the ventilation fan can move around the energy from outdoors to indoors, or basically remove from indoors to outdoors. Now the question is, when the ventilation fan is doing that job, we can afford the luxury of over-ventilating the buildings. It means that it would work in 100% fresh air mode about 3/4 of the year, 70%, depending on the climate zone. What is interesting is we do not recirculate. It means that we don't spread communicable disease, and we remove the off-gassing that takes place from furniture, from drywall, or any other equipment that is producing off-gassing, or even simple cleaning that uses chemicals. We are removing a lot more efficiently.
I think in today's world, as you mentioned before with the pandemic, this is a super important point, that the air is not being recirculated. 70% of the year it's in recirculation mode, and it just lessens the risk of the transmission of
Right. That's an interesting point. There are 2 air changes that are required for many buildings according to American Society for Heating and Refrigeration. That's the ASHRAE ventilation code requirement. And what it means is in 24 hours, the air recirculates 48 times. So that is something that our buildings don't have. In fact, about 30-35% of our buildings operate in 100% fresh air mode without recirculation.
As far as integrating with ventilation designs that use HEPA filters or filtration specifically designed to prevent the spread of or reduce the risk of the spread of disease, those systems they can integrate them or put them in the building, and it's not a problem for our system to be linked with that type of system.
Well, you see, filters actually meant predominantly to filter, the dirty air, believe it or not, that actually comes from outside. There is some obviously dust and some other, particles floating around that filters can handle. But, conventional buildings do not have hospital grade, filtering. So the best cure is 100% fresh air and no recirculation. And that once again, that's why the outdoor dining today is acceptable, while indoor, let's say restaurant dining is not quite ready yet. Because they need to fix the ventilation systems. So in our case, our buildings are doing great, and they can be fully functional as soon as people are ready to come in anytime today.
I'm going to move on to the third question. What types of floor coverings and ceiling treatments work with integrated ventilation design? Are there special ceiling treatments or rugs? Do they have to be certain kind of rugs? How does that work?
So with the flooring, we can use pretty well any kind of flooring coverings or systems that are being used right now. If carpets are used, then they should be suitable for radiant floors. It means that they would not trap the energy flow. So regarding ceilings, we prefer exposed ceilings. However, floating ceilings are fine because we may have some instances where there's quite a bit of concrete exposure. Acoustical panels on the walls could be required, or some other acoustical treatment could be required, but that is subject to specific designs. It can be done at the initial stage, or in speculative spaces, for example, it can be added, as part of the tenant improvement.
What types of buildings are the best application for integrated ventilation design?
Well, it's a large variety of buildings that can be suitable. To name a few, institutional buildings like schools, colleges, universities, municipal buildings, office buildings, nursing homes, high-rise residential. It's a large variety. You see, when we add smarts to concrete or precast, we open up interesting opportunities to view it as an asset that fits into better energy management and improved indoor air quality and energy efficiency, and a very efficient carbon cutting device that allows to reduce the carbon footprint of the building without introducing any complicated and costly mechanical equipment or insulating buildings.
So there's not really much of a limitation on what type of building this integrated ventilation design can be used in. Is that correct, Jack?
That's true.
Which climate zone is best for integrated ventilation design? Is there a limitation on that? Is it better in some and not so good in others?
We have buildings in cold climate, we have it in hot, and we have it in hot and humid climate zones. So it's just a question of engaging the mechanical systems that are suitable for this climate zone with the concrete floors or precast floors to extract value that is otherwise lost.
So most of our buildings are in climate zone 7, which is a colder climate. The baseline performance of our buildings has generally been net zero ready. Warmer climate zones, like climate zone 4, we have a building in South Carolina. It's just ideal situation for integrated ventilation design due to temperature differences from the day to the nighttime.
Many places in California, for example, can be in a ventilation mode without supplementary heating or cooling, because the temperature swings between day and night are amazing. Nighttime chiller-like temperatures are right there for the ventilation fan to pick up and move into the building. It creates an amazing business case. The issue probably would be not much with our technology, but with the building departments that would be puzzled. How can a building exist without heating and cooling equipment?
I like to say that the only reason that an HVAC system would be required in California climate zone would would be because of the local codes.
When we look actually at the building management systems, how they perform under extreme hot or extreme cold conditions, the proof is there. It's data-driven feedback.
Is there a noticeable difference in comfort and indoor air quality when compared to other ventilation designs, such as forced air systems?
Yes, it is. And the reason being is because our prime time is nighttime, and we leverage the difference in energy during the night and during the day, as well as the outdoor air quality at night is considerably better than during the day. What's happening is the nighttime freshness is actually brought into the building. And in a medical building, when they walk in the morning, the indoor air quality inside is better than outside. And they really are quite pleased with noticeable difference. The indoor air quality, it's one of those things that you have to feel it. It's measured event on building management systems, but to really experience it, you have to feel it.
We had some people from an architecture firm that went to University of Windsor, where we did one of the buildings, and they really had difficulty in describing the quality of the indoor air. They used to come to that building specifically to study and spend time because they said it felt so good, even though they really couldn't describe why or how. It just has a unique quality to it that makes people really like to spend time in the environment there.
You can have great interiors and nice wall and floor finishes and ceilings, but if the indoor air quality is not the best, then the total feeling of the space is totally different.
This is a frequent question about mold, condensation, and humidity. How does integrated ventilation design prevent mold and condensation in the building, Jack?
That's quite interesting. As we work in collaboration with mechanical engineers designing heating and cooling systems, usually the issue of humidity is dealt with at the source. It means that mechanical engineers know how to treat the air to remove the excess of humidity. That prevents the humid air or the moisture to enter inside of the building. Regarding the condensation that people sometimes feel it could happen inside, it never happened. So if it's dealt properly at the entry to the building by conventional designs, which are fairly standard, we never had any issues with mold, mildew, condensation at all.
Thanks for answering the questions, Jack. That's all the time that we have today. I'm very interested to hear your comments and feedback. If you have any further questions, we're happy to have a discussion with you. Thank you very much for attending and hope to hear from you soon.
Thank you, Tom Machinchik, for your presentation on behalf of ThermoBuild. I wanted to mention that CPCI has an extensive library of publications available for AEC professionals, and much of the information from this presentation came from these resources. These include the Architectural Precast Concrete Walls Best Practice Guide, the CPCI Design Manual, the PCI Architectural Manual, the CPCI Color and Texture Guide, and much more. All of these resources are available at cpci.ca under the Technical Publications page. In addition, CPCI has a monthly e-newsletter called CPCI Design and Building Express. We encourage you to subscribe to receive industry updates and free CPCI resources. You can sign up for the newsletter by going to our website at cpci.ca. Lastly, CPCI offers a membership category for professional firms like architectural and engineering firms, for example. By becoming a member, you'll receive many benefits. The membership application and additional information is also available on our website at cpci.ca under the section that is called Members. If you have any questions or comments for CPCI, please contact us at info@cpci.ca. Thank you.